of minus 3 n squared pi squared t over pi squared, which we probably could, n squared pi squared over n squared pi squared over pi squared, which I could write more civilized as exponential of minus 3n squared t, yeah? All right. So we started out with a separation of variables, led us back to the kind of boundary value problems that I told you would be interesting. And so what have we done so far? At the moment, all we've done is to construct solutions which do what? What part of the given data do they satisfy? They satisfy the partial differential equation itself. They satisfy the boundary conditions, right? But what about the initial condition? Not so much, right? Not so much. So, in summary, though, we have, I'll put it over here. Let's say un of xt equals to e to the minus 3n squared t cosine of nx, right? And then here's so what about the initial conditions? How do you fit initial conditions? And so here's what's bothering me, guys. If I partial differentiate x, I get 1, which doesn't fit the boundary conditions. And I don't know, does the initial condition have to fit the boundary conditions? Is it okay to have initial conditions which are not subject to the boundary conditions? It just worries me, and I should know this, but I mean, it is a problem in the book. It's problem number 3 from page 624 of the particular year of the book I'm looking at. It's got this lovely blue cover. 6th edition. That's what I found today. I don't know. I somehow feel better if I put a 1 here, you know? But then then at least the initial, I don't know. I mean, this is not your problem, all right? Like, this is not a problem that's asked of students. What are allowed initial conditions given a set of boundary conditions? At least I haven't seen that question yet. It's a question I'd like to ask, though, myself. So what do we do? Suppose, I'm not sure if it should be x or it should be 1. How would we fit that? I mean, does it work for this? You know, what's un of x0? What's that equal to? Well, cosine of nx, apparently, right? Can you get that equal to 1 or x for any choice of n? The answer should be an emphatic no. Definitely not. Right? That's a trigonometric function, and you've got 1 or x on the other side. Those are not trigonometric functions. And this is where the genius of Fourier came to bear. What Fourier's idea was, he said, you can write f of x as sum of sines and cosines. Just use infinitely many of them. Just keep adding sine after sine after sine, or cosine. Now in this one, so what we're going to do is we're going to propose that our solution is actually of the form, we're going to say that u of xt should be equal to the sum, n equals 1 to infinity, of the appropriate coefficients. Call them whatever you like. I'll call them c sub n for the moment. C sub n times the e to the minus 3n squared t cosine of nx. So this is sometimes referred to as a formal solution. I think I've referred to it as the, I'm trying to remember, right? One of these are there I called a blank template solution in previous years. And I like that terminology. I need to go back and look and make sure I'm consistent with my previous terms. But allegedly, if we believe Mr. Fourier, we can select coefficients C sub n to make this infinite series of cosines match up with the initial conditions. Because if you plug in 0, what do you got? Right? Supposedly this is going to be equal to, let's suppose it's equal to 1. Oh, and I forgot something. I'm an idiot. We definitely want x. We definitely want x. Forget about my 1. Let's put an x there. It's more interesting. The thing is, I forgot about n equals 0, right? So 1 is an allowed solution. I mean, 1 doesn't need the Fourier technique. If you just put 1 here, this is really, really stupid, but if you put 1 here and just erase the 0 and put a t, that solves this problem. And as such is not an interesting problem. So putting x here is more interesting. Although it makes me nervous for some reason. All right. Okay. So then what? How do you figure out what Cn is? Well, let me tell you something. If you integrate where'd you go? Oh, there we go. That doesn't help me. Integral from 0 to pi of cosine nx times the cosine of, let's say, px dx equals to zero if p is not equal to n, since the cosine of theta times the cosine of beta is equal to what? 1/2 what? Sine of theta plus beta, 1/2 sine of theta minus beta, something like that. I forgot, like plus or minus here, plus or minus there. I don't remember exactly, but there's a relation like this, right? It ends up being the sum or difference of the angles of the cosines being producted. And the thing is, if you integrate, sine from, not sine, listen to me. Cosine, right? Can you guys tell me? Anybody remember whether I should have a plus or a minus? I mean, I can work it out, take 3 minutes, but I don't have those 3 minutes. The bottom line is you get something like very close to this. Let me put some quotes on it just to be safe. All right? And so when you integrate this, what happens? When you integrate that with theta equals to nx and theta equal to px, you get sine of a sum or difference of integer multiples of x. When you plug in pi and 0, it's all 0. On the other hand, what happens if n equals to p? You've got cosine squared, right? And if you integrate cosine squared from 0 to pi, you get pi over 2. So that's the cool thing. If we go back to the problem we have, all right, and we just take this, right, take this and integrate the series, this trigonometric series, which is called the Fourier series in honor of Fourier. And we're going to just multiply the series by cosine of px, integrate from 0 to pi dx. And on the other side, integrate from 0 to pi x cosine px. Right? On this side, we end exchanging the order of summation and integration. We get the sum n equals, oh man, I'm sorry guys. I really should be doing sum n equals what to what. I need to allow for the constant term. I should have this starting at 0, okay? I'm supposed to be starting that at 0 because the constant solution is a possible solution to case 2. All right, so anyway, we've got Cn cosine of cosine px, cosine nx dx, and so what this ends up giving us is just Cp times pi over 2 equals to whatever this works out to. Right? So you can work that out. This is my dv, this is my u. Integration by parts says 1 over p x sine px evaluated from 0 to pi plus 1 over p integral of sine px dx from 0 to pi. This piece all 0. That piece minus 1 over p squared cosine of px evaluated from 0 to pi. So I get minus 1 over p squared times minus 1 to the p minus 1. So there you go. My Cp is actually minus 2 over pi p squared times minus 1 to the p minus 1. So you can take that, plug it back up in here, go back to my formal solution, plug it in there, and that is the solution built with infinitely many cosines. This is the so-called Fourier technique. Now, this thing I just did of integrating both sides and exchanging the sum, this is all formalized and made nicer with like theorems and some nice sort of formal developments in sections, I think 10 point, I don't know, what was it, 10.3. There's a section on Fourier expansions, 10.4, 10.3, and so there we actually come to some more sort of like organized thought process. I'm kind of out of time here, but this is it. I mean, this strategy I just showed you will essentially work for all 3 problems I've showed you. We separate variables, plug in the boundary conditions, pick from one of our 4 cases, we build an infinite set of solutions, and then the Fourier technique will allow us to pick coefficients to match the initial conditions. Something like that is how we solve all of these. So you guys usually ace this part of the course. I usually give a couple take-home problems, and by the time we're done with it, most of you don't lose points in this part of it at all. So, and I think it's interesting too. I love this part of the course. So anyway, I shut up. Have a good weekend, I suppose. Thanks, Joseph.